once again the second class of satellite communication. So in the previous classes, we have gone through some of the history of satellite communication and particularly the history of Indian satellite, which has been launched by Indian space research organizations. And we also have come across some fundamental things and some laws of satellite communication. So previously we have discussed two laws of satellite communication, which was given by Kepler. That is first law of satellite communication. He said the planets orbit in elliptical path with sun at focus, which is same for satellites around the Earth. In second law, he stated the line joining a planet to sun sweeps out equal space in equal time. That implies, in other way, we can understand that the velocity of satellite is lower at apogee and higher at perigee. So velocity is lower here means it covers less distance for some certain time duration t. Velocity is higher means higher in perigee. That means it covers more distance for the same time interval t. So there is difference in the distance covered by the satellite at two different points. Those are apogee and perigee. However, whatever may be the distance covered, but the area swept by the satellite is same for same time interval t. So from this we derived one conclusion that when the satellite is located at apogee, it travels with less velocity, and when the satellite is at perigee, it travels with high velocity. So these are two laws of planetary motion given by Kepler. In the third law, he gave the square of the period of a planet. The square of the period of a planet is proportional to the cube of the mean distance from the sun. Okay, so that means mean distance from the sun is r. It is proportional to the cube of the mean distance. So how it has been derived? So let us see the derivations. So when a satellite is moving or any object is moving around something, for example, we know if you remember, I don't know whether you have done in our childhood, what we do, we just take a stone and tie it by using a thread and keep it rotating like this. And the stone which is tied by this thread, it will keep on rotating as we move our hand like this. So there are two different forces are acting. One is centripetal force, another is centrifugal force. So one is outward force, another is inward force. So when two forces will balance with each other, then only the object that is your stone will keep on rotating as you rotate. If any of the force will be higher, then there will be some disturbances. If the outward force will become higher than the inward force, then your thread will break down and the stone will go away. So if we want any object to rotate continuously in a proper manner, then there should be a balance in between two forces, inward and outward force. So that is, a balance should happen in between centripetal force and centrifugal force. So this outward force we represent by mv square by r, where m is the mass of the body in kg. So body in the sense what? It is the body means suppose our satellite is rotating. So satellite is the body here. So body of the satellite, that means weight of the, sorry, not weight, mass of the satellite in kg. Then v is the velocity at which the satellite is moving. And the unit I am taking here, the kilometer per second. So mind the unit. Don't make mistake in unit, otherwise everything will become wrong. R is the radius of circle in kilometer. So what is the radius of circle? What do you mean? I mean the radius of circle means it is the radius at which the satellite is moving. Okay, so this is suppose our Earth and the satellite is moving like this. Okay, your satellite is moving here. So this is the radius of circle. So radius of circle means this particular circle, the orbital circle. So what is the radius? Radius means the center point. This is the radius. Okay, let me draw it properly. That option is not. Okay, so when I said radius r, so radius means it is the radius of this circle. Okay, that means center point of the circle. So if you notice here, when I consider the center point of circle, it also include the center point of your Earth surface. So this radius is nothing but the summation of Earth radius. This is your Earth radius plus what altitude the satellite is located from the Earth surface. You should understand this. When I mean the radius of circle, so radius of circle means it is the summation of Earth radius as well as the altitude of the satellite. Okay. Now coming to the centrifugal force. The centrifugal force we express by MA, and where F in is equal to M mu divided by R square, where mu is equal to G into M. G is the gravitational acceleration due to gravity. M is the mass of satellite. So sorry, it is not mass of satellite, it is the mass of your Earth. So these two are constants, so we have put the values. So mu is a constant. Always remember the value of mu because this value will not be given. So it is 3.986 into 10 to the power 5 kilometer cube per second square. Now let us balance these two equations, F out and F in. If you see here M and here M term will be cancelled out. Fine. So I am balancing here. So you see F in equal to F out. So V square, you see here, what you will have, if you balance, you will have V square divided by R is equal to mu divided by R square, because M and M are cancel out. So this R and this R will cancel and you will get V square is equal to mu divided by R. So that is what has been written over here. V square is equal to mu divided by R. So from this we can write that B is equal to square root of mu divided by R, where mu is a constant, the value is we have given, and R is the radius of the orbit in which your satellite is moving, and the unit is kilometer per second. The velocity is, the unit is kilometer per second. Okay, so this is the expression of velocity we obtained assuming the satellite is moving in a circular orbit. Keep it in mind. We have assumed the satellite is moving in circular orbit. So if the satellite is moving in circular orbit, then how much time the satellite will take to make one revolution? This is your satellite. Okay, this is the orbit. If you assume your Earth is located here at the center. So one revolution means it is 2 pi r. The distance covered with one revolution is 2 pi r. So this distance divided by the velocity, that gives us what is the amount of time your satellite takes to make one revolution around the Earth. So we have here the value of V, that is given over here. So from this t, we can express that t square is equal to square of this, that is 4 pi square r square divided by v square. So 4 pi square r square divided by v square. So we know that v is equal to this. So v square we can write v square is equal to mu divided by r. So in place of v square we can put mu divided by r. So r will come to the numerator. So it will be multiplied with r square. So it will become r cube. So what we are getting 4 pi square r cube divided by mu. And finally, if you see here 4 pi square, it is constant. Mu is also constant, which the value is 398,600 kilometer cube per second square. So this particular term, this is constant. So what we obtain that this t square is directly proportional to the cube of the radius of the orbit. So this is what was the third law of Kepler. Let us go back. So this one. So what Kepler say in his third law, the square of orbit of a planet is proportional to the cube of the mean distance from the sun. So when it is says mean distance of the sun, if it is valid for any object or any planet which is moving across any object. Suppose Earth is moving across sun, so the same planetary motion is applicable for Earth also. When moon is orbiting across Earth, then the same planetary motion is applicable to Earth also, or for moon also. And when the satellites are moving across Earth, it is also applicable for them. Now, this we have calculated when the orbit is a circular orbit. Now, if the orbit is an elliptical orbit, then what about the third law of Kepler? So for elliptical orbit, the value of v square will be given by mu into 2 divided by r minus 1 by a. So what is a here? A is called the semi-major axis. So semi-major axis is what? So suppose this is an elliptical orbit and the Earth is located somewhere here. This point is called perigee. This point is called apogee. This distance from center of the Earth to apogee is called RA. The distance from center of the Earth to point perigee is called RP. So A is nothing but A is equal to RA plus RP divided by 2. So this is called A. And where R, the value of R is the instantaneous distance from the center of the Earth. Suppose your satellite is located at apogee, then the value of R is equal to RA. If the satellite is located at perigee, then value of R is equal to RP. If the satellite is neither located at apogee nor located at perigee, but the satellite is located somewhere over here. This is the location of your satellite. Then what is the value of R? In that case, R is equal to this much. It is the instantaneous distance from the center of the Earth to the orbit, or that is also called as R is called as the orbital height of the satellite. So in this case, as the location of the satellite will change, the R value will change, whereas A value will be fixed. If the orbit is fixed, A is fixed for an elliptical orbit. So in that case, you will have the value of B square, that is 4 pi squared into A cube divided by mu. Now let us take an example and see what we are see. Assume that orbit is a circular orbit. Question is to find the velocity and period, that means time period, in circular orbit for orbital height is 1000 kilometer, 20,000 kilometer, and 40,000 kilometer. So what you have to find? Given orbital heights are given, and given the orbit is a circular orbit, it is a circular orbit and orbital heights are given. So orbital height given means R value is given. So we have to first find out what is the velocity. So for which formula we shall use? We shall use this formula. V is equal to mu divided square root of mu divided by R. R value is given. Mu is constant that we have seen. So using the different values of R, we can calculate the velocity at which the satellite is moving at different orbital height. So what we are getting, you see just. So for 1000 kilometer of orbital height, the velocity at which satellite is moving, that is 19.96 kilometer per second. When the orbital height is 20,000 kilometer, the satellite is moving at 4.46 kilometer per second. When the orbital height is 40,000 kilometer, the satellite is moving at 3.15 kilometer per second. So what do you mean by that? When the satellites are moving in the lower Earth orbits, that means close to Earth, they are moving at a very high velocity. But when the satellites are located at a very high altitude, then they are moving at very low velocity. Okay, and similarly, this time period you can find out from this. Once you calculated the velocity, because R values are given 1000, 20,000 and 40,000, V you have calculated. From this you can calculate the time period. So what we obtain that when the satellite is, suppose this is the Earth, this one is your Earth. So this orbit is 1000 kilometer orbit. This orbit is 20,000 kilometer orbit. And this orbit is 30,000 kilometer orbit, right? So the satellite which is here at 10,000 kilometer of altitude or orbital height, it moves at a velocity that is much higher in comparison to the satellites which are moving at high altitude orbits. And hence the time period. So the time period means it is the time taken by the satellite to make one rotation across the Earth. So here the time taken to make one rotation is 314.5 seconds, which is around 315 seconds. So in 315 seconds, a satellite can complete one rotation across the Earth. That is nothing but, so 315 seconds, it will be approximated by 5 minutes or more than 5 minutes. So in 5 minutes, the satellite which is located at lower Earth orbit, they complete one rotation across the Earth's surface. Just imagine how fast they are moving. Whereas the satellite which are moving at high altitude orbit, they are taking so much time, around 80,000 seconds to complete one rotation. Okay. So that is the idea which has been derived from the third law of Kepler. So what is the problem is that problem happens over here. So what is this is approximately 5 minutes. Okay. So see, if a satellite is here and your ground station is here, when the satellite is here, they can communicate with each other. And after 5 minutes, since the satellite will take 5 minutes time to make one revolution. So most probably after 1 minute, the satellite will be somewhere here. Next minute, the satellite will be here. Next minute, the satellite will be here. Next minute, the satellite will be here. And in 5 minutes, it will be again come back to this position. So what difficulty we are facing at this particular point, that in 1 minute, the satellite has gone out of our vision. It is not particular the vision, the satellite has gone out of our coverage area. Means if the satellite was here, then we can make a communication between our ground station and satellite. But when the satellite moves to this particular point, then the coverage of the satellite will be somewhere here. So this point will not be in the coverage of the satellite. So within 1 minute, the satellite disappears. Then how we can maintain a continuous communication? If within 1 minute, the satellite goes away of the field of view, then how we can make a communication? So how this uninterrupted communication can take place for such satellites which are moving at a very high velocity? So there are two different solutions for that. So for solution number one says, for continuous visibility, either put large number of satellites in low Earth orbit. Low Earth orbit means the orbits which are present very close to Earth, which is 1000 kilometer approximately. So in that case, you have to launch more than one number of satellites, so that if any particular satellite goes, the next satellite will come. So that we can maintain, if that satellite goes, then another satellite will come to that place. So by launching a series of satellites, we can make an uninterrupted communication. We can establish an uninterrupted communication. Or else we can go for another option. The second option is make it relatively stable with respect to Earth. That means this particular satellite will become relatively stable. Suppose this is our ground station. What is relatively stable? You know what is relativity? What is relative motion? What is relative velocity? You know. So have you watched a movie that is Ajay Devgan's that is called Himmat Wala or something like this? I don't know that movie exactly. Where the Ajay Devgan is riding over simultaneously two bikes. One of his leg is on one bike, another leg of his was in other bike, and he was standing on this without any disturbances. So how it is happening? His Ajay Devgan is relatively stable, and it happens only because two bikes are relatively stable with each other. Because when two bikes are moving at equal velocity, then the relative velocity will become 0. So they are relatively stable. So that concept we can apply here. If the velocity at which the Earth rotates itself at the same velocity the satellite will move in its orbit, then these 2 points, this point which is the ground station on the Earth and this is the satellite, they will focus with each other at every point of time throughout the year. So this is called relatively stable. So that a continuous communication link we can establish throughout the year and throughout the life of the satellite. So that is what satellite apparently remains stable with respect to an observer on the Earth. So this observer we are considering as the ground station. If satellite orbit period is made same as that of the Earth revolution around its own axis, then the ground station which is located on the Earth's surface, it can establish a continuous communication. So when the Earth rotates itself and when it completes complete one rotation, we called it as a day. That is true. What is a day? Question comes, what is a day? Then you can think that why I am asking this question, what is a day? Because the question is very important. In satellite communication, it is very difficult to decide a day. What we call a day? See here in this particular image. This is the sun. This is the planet, which is your Earth. The planet, our Earth, rotates around the sun, as well as our planet Earth rotates around itself. So when suppose one point on the Earth's surface, this which is the line joining between the center of the sun and the center of the Earth, so this point is P. So this particular point P is completely focusing to the sun. So that if we make a line joining from the sun center to the Earth center, then this point P will cross, then this line joining will cross at the point P. So this point P, it is exactly lying on the line joining between these two centers. So that means we can say the point P is completely focusing towards sun. Now, when next what happens? The Earth rotates itself as well as rotates around sun. Now, when the Earth next time moves at this particular point, suppose I will take example that the Earth is now here. This is your Earth. Next time the Earth is here, and your point P has come to this particular point. This location P has moved because your Earth is also rotating around itself. Okay. So at 180-degree rotation, the point P has come to this point. Now, when the Earth makes 360-degree rotation, the point P is at this particular point. So starting from this to ending again at this point, that is 360-degree rotation. Is it a day? But if you see, when the Earth completes 360-degree rotation, the point P is not focusing towards the sun. If you make a line joining between the center of the sun to the center of Earth, then the point P is lying out of the line joining that. But in what we call a day means what? Today morning to next day morning is one day. Today noon to next day noon is one day, or we can say today night to next day night is one day. But if in that case, when the Earth completes one rotation, it is not noon, but we can call it as a forenoon. So there are two different days are there. So one is called, you see here. Now, when the satellite complete more than 360-degree rotation, this particular point P will move this point because it is moving in this direction. In this direction, it is moving. So now this point P is focusing towards the center of the sun. And here at this point, you are having noon. So this point, at this particular point, you had noon. Next day noon is happening at this point. That means in that case, your Earth is moving more than 360-degree. It is not exactly 360-degree. So one rotation does not mean a day. A day is more than one rotation. And so that is why there are two different days are there. So one is called sidereal day, another is called solar day. So this is called sidereal day. This is called solar day. So when your Earth completes 360-degree rotation, so that we called as a sidereal day. But when from today noon to next day noon, in that case your Earth rotates more than 360-degree, that we called as solar day. So solar day is equal to 24 hours. So sidereal day is not 24 hour, but it is less than 24 hour. That is equal to 23 hour 56 minutes and 4 seconds, which is equal to 84,164 seconds. So this is called sidereal day. That means when the Earth complete one rotation, 360-degree rotation, it does not take for 24 hours. It takes 23 hours, 56 minutes and 4 seconds. But a solar day means it completes more than 360-degree rotation, that we call today noon to next day noon, or today morning to next day morning. So like that, we consider this as one day, which is called a solar day. So solar day and sidereal day are two different things. In satellite, we are not considering solar day, we are considering sidereal day, because we are considering one rotation across the Earth's surface. When our satellite complete one rotation, suppose assume this is the orbit of the satellite. So when the satellite was here at this particular point, and when it completes one rotation at exactly this point, that means when it completes 360-degree rotation, so that is called a sidereal day. Okay, so which is equal to 84,164, or you can remember otherwise at 23 hours 56 minutes and 4 seconds. So this is the time taken by the satellite to make one rotation. Keep it in mind, not all satellites. I am telling, not all satellites takes this much time to make one rotation. Which satellites take this much time to one rotation? Because in the previous example, we have seen we have seen some satellites are taking 300 something time, and some satellites are taking 79 or around 80,000 seconds to complete one rotation. So different satellites takes different time to complete one rotation. So which satellites take this 84,000 second to complete one rotation? What is the answer? So this is the time. This is the time that is called sidereal day. So what is a sidereal day? Sidereal day is a day when the Earth complete 360-degree rotation. That is called sidereal day. So which satellite takes this much time to complete one rotation? These are the satellites which we discussed this year. The satellites which are relatively stable with respect to Earth. At what speed your Earth is rotating, if the satellite will rotate at the same velocity, so that they will be relatively stable. So those satellites which are moving at a velocity equal to the velocity of the Earth, those satellites will take 84,164 seconds to complete one rotation across the Earth. I will tell what those satellites are called after some seconds or some minutes. Yeah, come to the point. What is the orbital height of a circular orbit satellite with period of a sidereal day? So what is the orbital height? Use this particular equation, because in the previous derivation of third law of Kepler, we established this relationship. Okay, so what we established there, I have to go back. Yeah, here, remember this. T square is equal to 4 pi square r cube divided by mu. So from this, I can write r cube is equal to mu into t square divided by 4 pi square. Okay, or I can write r is equal to root cube of mu t square divided by 4 pi square. So this is the expression of the orbital height of the satellite when the satellite is moving in a circular orbit. So this is the equation which has been written over there. So r is equal to cube root of mu t square by 4 pi square. Is it here? Now use this equation. So question is, what is the orbital height of a circular orbit satellite with period of a sidereal day? Okay, come back to the previous slide. In the previous slide, as what I said, our Earth takes this much time to complete 360-degree rotation across itself. And similarly, some satellites, they also take this much time. So which are those satellites and what is the orbital height of the satellites? So what do you mean by orbital height? It is the distance between the orbit to the center of the Earth. So this is called the orbital height. That means the question in the next slide is, if the satellite is taking this much amount of time to make 360-degree rotation across the Earth, then what is the location of those satellites? That means at what altitude the satellite is located? That is the question. So if you use the value of t is what? This t we have got from the previous one, 84,164. It is 84,164. Mu is constant, 4 pi square is constant. If you put the value, then it will come 42,164. So this is the orbital height. That implies if this is our Earth, and this is the orbit of your satellite, which is rotating around. This is the satellite which is rotating around the Earth. Then the orbital height is this much. That means from this point to this. So this length is equal to 42,164. But when it is said what is orbital height, so it includes this much distance also. That means from center of the Earth to Earth surface. So that is the Earth radius. So Earth radius is included. Then from Earth surface, how much is the distance of the satellite, or what is the altitude of the satellite from Earth surface? That is nothing but you have to subtract the Earth radius. So you remember this value. Nobody is going to tell this value. The radius of Earth is 6,378 kilometers. So subtract this radius of Earth from this, then you will get 35,786 kilometers, which is equal to this much. So from Earth's surface at an altitude of around 36,000 kilometers, if a satellite is located, and those satellite will take one sidereal day, that is equal to 84,164 seconds to complete 360-degree rotation. I repeat again for your understanding. If a satellite which is located at 35,786 kilometer altitude from Earth's surface, not from Earth's center. If you talk about the Earth center, then this is the value, 42,164 kilometer. Okay, from Earth's surface, if a satellite is located at an altitude of 35,786 kilometer, those satellites will take 84,164 second time to complete 360-degree rotation around the Earth's surface. So 84,164 seconds is the time taken by the satellite to complete one rotation across the Earth, and 84,164 seconds is the time taken by the Earth to complete one rotation, to complete 360-degree rotation around itself. Can you explain the question again? Which question? This particular question, which is in front of your screen, or the previous question? Okay, this question. Okay, so come back to the previous slide. So what we understood in this particular slide, when we talk about a day, day does not mean that today morning to next day morning, or today afternoon to next day afternoon, or today noon to next day noon. So that day is called a solar day. So one solar day does not mean that the Earth is rotating 360-degree around itself. No, that is wrong. When your Earth completes 360-degree rotation, starting from this particular point, so starting from this particular point is just, suppose this is not a point, assume that some person is here. So P is a person. So P is nothing but it's me, which is I am standing on this Earth surface at this particular point, and sun is just above of me. Okay, you can see this sun is just above of my head. So I am not changing my position. The Earth is rotating around the sun as well as around itself. Then P came here. That means it became afternoon or it became evening. Then it became night. Again, the Earth is rotating. It became good morning. Again, at this point, it became noon, and the sun is again come to my head. So when that means when again sun came to my head, we call it a day. But that day is a solar day. That day is a solar day. But if you see, when the Earth is rotating, it is this P point is moving like this. So when this P point is completing, when it completes 360-degree rotation, it is not pointing towards sun. Okay, it is pointing somewhere here, because 360-degree rotation means it will again come here. So it is not pointing towards the sun. So sun is somewhere here. So this point is called, we can call it as a forenoon. So 360-degree rotation, that does not mean it is a solar day. So solar day is more than 360-degree rotation. That means when Earth completes more than 360-degree rotation, so that is a solar day, and that solar day is called 24-hour. Okay, that means today noon to exactly tomorrow's noon, that is 24-hour that we fixed our clock. But sidereal day is when it completes 360-degree rotation. That is called sidereal day, so which is less than solar day. So this is what the observation we got. Our Earth takes how much time? 84,164 seconds to complete 360-degree rotation. Okay, now that is the Earth, what it does. Now think about the satellite. This is a satellite which is rotating around Earth. But the satellite is not rotating around itself. Satellite only rotates around Earth. It is not rotating around itself. Correct. So when the satellite is here, okay, so the Earth takes this much time, this much second of time to complete 360-degree rotation. Now, if the satellite will take the same time to complete 360-degree rotation, then the satellite will become relatively stable with the Earth. So as this point P is moving like this, the same way the satellite will move like this. So suppose the satellite is not here, the satellite is here. Okay, so if your satellite will take this much of time to make 360-degree rotation, then this point P and this satellite, they will become relatively stable. That means suppose P is myself, I am the person which is P, I am standing on Earth's surface, every time I will see the satellite which is on my head. In the night also I will see the satellite on the head. In the morning I will see the satellite on the head. In the noon also I will see the satellite on my head. So that is the idea, that if the satellite can rotate at the same velocity, and if the satellite will take the same time that the Earth is taking, then they will become relatively stable, or they will become synchronous. That is the idea, to make relatively stable. So with that idea, we are coming to this particular example. So this particular example is, what is the orbital height of a circular orbit satellite with period of a sidereal day? That means, if this is the condition, then what is the orbital height? That means this particular satellite is located at what point, at what altitude. So that means from point P to this orbit, how much is the distance? So that is the question in the next slide. Okay, so we use this equation of third law of Kepler. So here T is given 84,164 and rest of the values are constant for us. You can easily calculate, it is coming around 42,164 kilometer. So keep it in mind that when we are calculating this R value, I told it very beginning. If you see, I told in the very beginning where I told, here I told here that when we are calculating this R is always the distance from center of the earth to the orbit. So that means we are including the radius of the earth. Don't do mistake. So what the value we are getting, this value is including the center of the earth. That means this much is included. Now then this is your earth. This is the earth. From a earth surface, how much is the altitude? This can be obtained by subtracting your earth radius from this value. So earth radius is 6,378 kilometer. So that you subtract from the obtained value. So that you will get as 35,786 kilometer. So that is the orbital height. So now if a satellite which is located at an orbital height that is around 36,000 or which is around 35,786 kilometer, those satellites are relatively stable with the Earth's surface. Because this satellite on Earth, they will take equal time to rotate to make one complete rotation. So that time is 84,164 seconds. They will take equal time to complete 360-degree rotation, and hence this Earth surface and this satellite, they will become relatively stable. And at this particular point, if you build a ground station, so your ground station and satellite throughout the year, they will keep on looking with each other. So there will be proper alignment between these 2 points. In no case they will be misaligned. So these satellites are called geosynchronous satellite, or that is called also in short, it is called GSO. So at this height, how much height? 35,786. It is roughly also called as 36,000. Roughly we call 36,000 altitude. So at this height, the satellite is moving in synchronism with Earth rotation. So those satellites are called geosynchronous satellite, or this orbit which is located at an altitude from ground surface, that is 35,786. From ground surface 35,786, or from Earth surface 42,164 kilometer. So this orbit is called geosynchronous orbit, or that is called GSO. So all right. So this is our discussion of today's lecture. We can stop here.